So our next speaker is Andrew Nemec, who is going to talk to us about SDP bounds on quantum codes.
Hello? Can you hear me? Okay. So this work is jointly done with Gerard and Felix. So this is technically Gerard's dissertation work, but he is stuck in Europe, so I get to present it for him. So since this is not in the error correction section, I thought I'd just review some stuff about quantum codes. So a quantum code is just a subspace of your Hilbert space, and we're going to represent it by a projector pi. Okay. When noise acts on the channel, you can correct the noise if the Krauss operators satisfy the Canilla-Flamm conditions, and basically all this means is that you want there to be a recovery operator that maps back to your code space up to some coefficients. All right. We say that an operator has weight has some weight where the weight is the number of coordinates where the operator acts non-trivially. So if we have this poly string ix izz, this has weight 3. And so one way to classify a goal in quantum error correction is we want to correct all tensor products of weight less than d, or I guess less than d over 2. Okay. All right. So one of the fundamental problems in quantum error correction, at least on the theory side, is given a block length n and a distance d, what's the maximal dimension of your code that you can have k. All right, and so we can rewrite this as a feasibility problem. So we want to find a matrix pi such that it's a projector, it has trace k, and it satisfies the Canilla-Flamm conditions for all correctable errors. So you want the product of any two correctable errors to have distance less than d. Okay. And so a code with parameters nkd exists if and only if this program is feasible. All right, so this is a hard problem to solve, so typically we try to do approximations. So, and so today we're going to be looking at upper bounds on the size of k. So, so from classical coding theory, we get famous analytical upper bounds, singleton bound, Hamming bound. These both have quantum analogs. Unfortunately, both of these bounds are quite loose, and in the Hamming bounds case, it doesn't even apply to all codes. So it's not known if the Hamming bound applies to, for example, degenerate codes in general. So if we try to move to bounds from optimization problems, typically we get sharper bounds. So this starts in classical coding theory with McWilliams's observation that you can connect the weight enumerator of a code with the weight enumerator of its dual code. Shor and Laflamme showed this was also true in the quantum case. And then from these McWilliams identities, this forms kind of the backbone of the linear programming bounds. So this was noticed by Delsart in the classical case and was done by Schickman and Litzen a couple years later, a couple years after Shor and Laflamme proved McWilliams' identity. So we want to get some tighter bounds, and so this was originally done in the classical coding case using semi-definite programs by Shriver, and then very recently in two independent papers in the quantum case. So this paper by Lay et al. They come at this from a classical coding theory perspective, so it only applies to stabilizer codes and their immediate generalizations, the code word stabilized codes. In our case, we come from more a quantum optimization approach, and ours applies to general codes, plus we get some additional constraints that they don't have, so we actually do get some non-existence results that can't be derived from their approach. Oh, yeah. All right, so just a reminder, the weight enumerator for quantum codes are defined like this. So in the stabilizer case, this counts the number of stabilizer elements in the code up to a scalar, and this counts the number of operators in the centralizer mod phases. So we can rewrite the Knoll-Flamm conditions in terms of the weight numerators. So we want to require that AI is equal to KBI for all weights less than D, right? And since we have the McWilliams identity that relates AI and BJ via the Krakow polynomials, we can rewrite the Knoll-Flamm condition only in terms of the A weight numerator. Okay, and then from this we can derive the quantum linear programming bounds. So our question is, can we get a semi-definite program that optimizes over these sorts of trace constraints that are quadratic in the state? Okay. So the main contributions of this paper are we show that a quantum code with parameters NKD exists if and only if a certain SDP hierarchy is feasible at every level. We show that the lavage number of a certain graph bounds the existence of self-dual quantum codes, and then if you symmetrize this, we get what we're calling the quantum Delsart bound. And then finally, we show that you can symmetry reduce our semi-definite program to one of size of order into the fourth variables using the Terwilliger algebra. And then so using this, we show that codes with parameters 714, 893, and 1054 cannot exist. So these aren't stabilizer codes. These are the K value represents the dimension of the code space. So, okay. So our key idea is to write a moment matrix. So EA is going to be the expectation of a poly where our state is going to be just our projector normalized so that it's a density matrix. And so we're going to construct a moment matrix whose entries are triples of these expectations. And so the indices here are going to be the polys scaled by their own expectation. So, for example, down here at the end, you'd have the poly ZZ with scaled by the expectation of ZZ. Okay. All right. So for a moment, we're going to restrict ourselves to self-dual codes. And so self-dual codes, they are pure, meaning that distinct errors in the correctable errors set need to map to orthogonal spaces. And what this gives us is constraints on our matrix gamma. So, gamma AB has to be equal to 0 if any one of EA, EB, or EA, EB is less than D, right? And in particular, if the code is, a code is self-dual, if and only if K is equal to 1, and by definition, we require that code to be pure. So for self-dual code, what we find is the top left corner is going to be equal to 1. The diagonal, the main diagonal, the first row, and the first column are all going to have the same values. And then finally, the sum of the elements on the main diagonal are going to sum to 2 to the n. So this actually corresponds to a hyperplane in a theta body. So a theta body is when you have a graph and you're trying to find the lavage number of that graph. The theta body is a set of feasible solutions to that STP. So in particular, this a matrix of this form is going to the theta body of a particular graph is going to be have exactly the form of the matrix that we get from a self-dual code. So the particular graph we find is what we're calling the quantum confusability graph. So this has the polys minus the identity as vertices, and if two edges or two vertices are connected by an edge, if the weight of their product of the corresponding polys is less than d, or they anti-commute with each other. And then finally, we have a self-edge if if that poly has weight less than d. So this is similar in the classical case, the classical confusability graph, but we now have this anti-commutation constraint that is counted as something that can be confused, right? And so from this we get a lavage bound on self-dual quantum codes. So if a self-dual code exists, then this theta body contains an element such that the sum of the diagonal is equal to 2n, and 2n has to be less than or equal to the lavage number of the graph plus 1. And so if one of these constraints fails, then you know that a code with those parameters can't exist. So you can use this to show that a 413 code doesn't exist. Right? Okay. So to just kind of formalize this, when EA and EB anti-commute, their expectation must be imaginary. But if gamma is a valid moment matrix and it's complex, then there's going to be a real valued matrix gamma plus gamma transpose over 2. And in particular, if gamma optimizes or is optimal, then this matrix will also be optimal, and it's real. So from now on, we're going to assume that gamma is a real matrix. And because of this, we can impose an extra condition that if two indices anti-commute with each other, then the element represented by them is going to be equal to 0. And in particular, this is going to be where we get a lot of our stronger bounds from compared to the classical case. All right, so we can impose further constraints on this gamma. So if we can impose structure constraints. We need to impose projector constraints that guarantee that our state rho is proportional to our projector. And finally, the Canova-Flamm conditions give us distance constraints. Right. So here this is our SDP, and here two elements are equal to each other if you can permute EA, EB, EA, EB into a different thing. And then down here we just have the normal Canova-Flamm conditions for distance. And you can derive these projector constraints using like a swap trick. So, all right. So to get a linear programming approximation of the lavage bound, we average over the distance-preserving automorphisms of the Hamming cube. And so this averaging will group together polys of the same weight together, and this gives us exactly the Shor-Laflamme weight numerator, or the weight distribution. And so this averaged lavage bound plus the extra constraint leads to what we're calling the quantum Delsart bound, which is basically the quantum linear programming bounds specialized for self-dual codes. And then if we go ahead and replace the self-dual code construction with the canola-Flom constraints, we can recover the well-celebrated linear programming bounds for quantum codes. Right? So this LP bound is what we call a 2-point bound because it's, in the quantum case, we view it as like overweights, but classically you can view it as automorphisms that preserve the distance between pairs of code words. And so this is an element of the Bose-Mesner algebra. It can be diagonalized. So that's where we get the nice linear programming from. All right, so if we recall our original feasibility problem, we can actually approximate this problem by extending our main SDP into a converging hierarchy. So this is done using state polynomial optimization, which is a variant of the NPA hierarchy. And this allows us to optimize over expressions that are nonlinear in expectation. So and this hierarchy is complete in the sense that any code with parameters nkd exists if and only if every level of the hierarchy is feasible. Okay. So we want to know, is it still numerically feasible to work with this hierarchy? And the answer is yes. We take a page out of classical coding theory, and we can symmetry reduce an intermediate level of the hierarchy to reduce its size. So we develop a 3-point bound, or at least we follow Guys, White, and Shriver, and Tanaka. And this average matrix is going to be an element of the Terwilliger algebra of the Hamming scheme. So this groups terms derived from pairs of polys. So we, instead of just having one poly and looking at its weight, we look at 2 polys, their weight, and then information about where they intersect. And so this reduced SDP has a quartic number of variables, and these variables serve as the generalized weight distribution of the code. And so all the constraints we derive for gamma can be averaged to obtain constraints on the symmetry reduced gamma. So this is a thing, because the Terwilliger algebra, it no longer diagonalizes, but it block diagonalizes, and each block is positive semi-definite. And what I want to point out here is that this constraint right here is our anti-commutivity constraint. And when you collapse this down to the linear programming bounds, T and P are both equal to 0. So this bound, this anti-commutivity constraint disappears whenever you're working with your linear programming bounds, right? So this is why this constraint hasn't come up before, right? And so using these symmetry-reduced SDPs, we get tighter bounds than both the linear programs plus the shadow constraints. And so we use the the symmetry-reduced version of the Lavage bound to prove the non-existence of a 714 code. So this was originally proven a few years ago by one of the co-authors on the paper using a different technique. But we have 2 new parameter sets that are now proven to have no codes with those parameters. And in particular, this means that the 2 stabilizer codes, this 833 code and the 1024 stabilizer codes, they're going to be optimal in dimension across all quantum codes. So, and then along with this, we produced infeasibility certificates for each of these STPs to certify that the result is in fact correct. Kind of just want to stress that the bounds given by Lay et al., they use the exact same techniques as us, but they came at it from a classical point of view. Since in classical coding theory, there's no such thing as anti-commuting letters in your alphabet, they couldn't get this bound or this constraint. So it shows the power of coming from this quantum direction. Okay. So contributions, we have a complete hierarchy of semi-definite programming bounds for the existence of quantum codes. we produced quantum analogs of the classical Lavage and Delsart bounds. And then finally, we showed that we can get numerically practical relaxations via the Terwilliger algebra. And we showed that, in fact, we get new non-existent results for certain parameter sets. And finally, future directions. You might have noticed that the McWilliams identities don't play nice with the 3-point bound. They're stuck with the 2-point bound in terms of the weight. We'll need to develop higher order generalizations of the McWilliams identity. And then we'd like to know if this sort of technique can be applied to other moment hierarchies. For example, there was a recent paper on sign weight enumerators for magic state distillation. So, if other people have ideas, that would be great. So, and I just wanted to end. So, this is Gerard's thesis work. He is currently looking for postdoc positions. So, if you are in Europe, give him a call or an email. And Felix wanted to say that he just won a grant, and he's looking for both postdocs and PhD students. And he's at University of Gdansk. So, yeah, thank you.
Question there?
Okay, I have maybe a couple of questions. So maybe the first one, just on the symmetry reduced thing with the Terwilliger algebra. So, I mean, maybe this is just a question for some intuition. So if I remember correctly, roughly in the classical case, when you get SDPs from this Terwilliger algebra, there's like some clear interpretation for these X things. They are like, you count like triangles of some equivalence class geometrically within the Hamming graph, and you only include triangles whose edge points are within, with the code words. So at some point, I tried to generalize this to the quantum case, right? Just to write down some weighted triangles, which didn't work immediately, and so my SDPs didn't work. So is there some intuition here for how, like, can I think about this as a sum over like weighted triangles in some way, in some intuitive way?
Maybe we weren't. Do you know where was that in the original Shriver paper, or
sorry?
Was the interpretation of the Shriver paper?
I think so.
Okay. So we have to do it over like an alphabet of size 4. So maybe the interpretation becomes more fuzzy there. So yeah, we hadn't seen that interpretation, but it's interesting. Yeah.
Okay. Then I have two other questions. One is, is there a way to get asymptotics out of this? Because I think it's usually very difficult. And
right.
then the other one is there like a version of these shadow constraints at each level of this hierarchy? Because you said your hierarchy includes the shadow constraints, but does it at what level of the hierarchy? And is there like some equivalent?
We just used. So to answer the second question first, we just used the normal shadow constraints. We didn't try to generalize, and this ties into the maybe it was a little misleading. This is the shadow constraints are with the LP bounds and the STP bounds, but they're the shadow constraints have the same problem that the Canola-Flom constraints have, in that they're inherently tied to the 2-point bound, right? So you're averaging. This is the exact same constraint as from the linear programming bound. So if we want to get better shadow constraints, we need to generalize the McWilliams identity, or I expect that generalizing the McWilliams identity would lead to better shadow bounds, more fine-grained shadow bounds. What was the first question?
I think I also asked something about asymptotics. Because,
we don't know. I mean, we also want to know the answer to that, but we're not sure how to go about that. So, yeah.
Yeah, thanks for the talk.
I wonder, can you write a systematic program based on your SDP hierarchy to rule out the non-existence of several codes, or just you find the infeasibility of dual problem?
We set it up as an infeasibility approach. So we had arguments or discussions over this. We weren't exactly sure how to deal with k being in the denominator here, because because normally in the classical you're trying to maximize over the sum of the elements. So we had discussions. We figured it was just easier to just leave it as feasibility, but if people are able to do that, that'd be great. So.
Okay, and the second question, how large can your numerical reach the n number of qubits?
I don't know the exact answer. I know that we can do it up to size 13, but there's a spot on the code table, like for, not for stabilizer codes, but for non-additive codes, that a length 13 code, and we were able to just have it tell us that it does not exist, but we couldn't recover the certificate for it. So we didn't want to include it. So we can get up to size 13. I'm not sure how far, Gerard did all the programming, so I'm not sure how far beyond that he got. So it's, still pretty low length. So.
Thank you.
Yeah.
Last question.
Thank you. So you showed that some of the codes don't exist, but I remember that the proof for 714 was extremely simple that Felix did.
Yeah.
So can you extend these proofs now that you know that 893 or these things don't exist? Or like it was based on state inversion and it was like few liners. So how come they don't work? Or can you comment on that?
Felix never mentioned that. I'm sorry. My guess is it might work, might be so simple because it's a single state and these aren't. So.
Okay, it's a whole subspace, you're saying.
Right. That would be my guess, but you'd have to ask Felix that.
Okay,
so.
I will.
Yeah.
So that concludes our session. Thank you all for attending and enjoy the conference.